Okay, so simultaneous multi-projection, which Jensen talked about yesterday. SMP for short. I guess SMP stands for some other things too, but we like to call it simultaneous multi-projection. So just to recap, kind of what Jensen talked about yesterday. We're always trying to look at where is the world going, right? That's our architecture should be inspired by our vision of where we see technology heading. And one of the things that we saw going in the development of Pascal was this change in displays, right? That idea for a single flat display that is where the original OpenGL pipeline from 800,000 years ago was designed. That's not the way the world has gone to, right? We have surround displays where you've got multiple displays to project onto, curved displays. VR, of course, is a big development. Now you've got actually a lens between you and the display. So the classical projection is actually just wrong when there's a lens in the way, because you actually have to project in a way that's the inverse of that lens in order to see the right thing on the other side. So that's the domain. And then looking beyond into the future, lenticular displays where you have a whole bunch of different projections that you can see. As display resolutions go up, I'd expect that's going to become an interesting scenario. Augmented reality, other kinds of scenarios. So what all these have in common is that it's just not the one simple projection. You're doing many projections. And the way you do that today is you have to just multipass it, right? If you need 8 projections, you run through all the whole work 8 times. You need 16 times. And that's not a good thing, right? That's not the right way to do it. And so we realized that it would be better if we built an architecture that enabled you to, in a single pass, stream that geometry through and then broadcast it out to each proper projection. That's what we did. So I wanted to go through the demo a little bit again yesterday that we did yesterday. Now, I think that Tom wants to do it. Do you guys think Tom wants to do it? You guys think? No. Come on, guys, let's get him up here. Come on. All right, he's coming in hot. All right, Tom. Okay, wait. The hug. All right. Oh, Tom. Okay. All right. Okay. All right. Okay. So Tom, let's fire. So Tom, if I can interrupt if I have anything to add.
Yes.
Okay.
It's a quick hug.
Okay. All right. Okay. Cool. All right. Okay. But so walk us through this, Tom.
Okay.
From the top.
From the top.
Okay.
Okay. So first of all, most of you guys understand how graphics work, but I'd like to just do a quick recap. Artists create these 3-dimensional models, right? So in this case, it might be a pyramid or square or a ball or whatever. And then they're placed in a 3-dimensional scene, right? And that's what you see in the background here, that kind of arc. It's the geometry, right? You all know about the geometry pipeline. Now the next thing that has to happen is that geometry needs to get projected to a screen so you can look at it. And that's what's represented by the green box. So this act of projection was very simple in the past, as Jonah said, right? It's classic, it's well understood, and that's why it was generally sort of fixed and very simple logic. And that's all changed because now monitors are getting different. So in this application, I can kind of move our position around and look at it. By the way, this is just a simulation. It's not accurate, right? It's not completely true, but it's illustrating the points, okay? So if you look at this, you can kind of move your viewpoint around, imagine you're looking around the world, but at the end of the day, it's a square and a single projection. But life has changed, as Jonas said, and so I'm going to try to show you that, right? This is the example we showed last night, and now instead of one projection, right, we've got 3 monitors. And what happens is the game has no idea really that it's 3 monitors. It thinks it's one projection. It's just a big wide projection, right? So, by the way, how you doing? Good. I haven't seen a long time. Yeah. So, again, you got this 3D math up there, right? Now, the cool part is the world does not change independent of the projection, right? The projection is the last part of the pipeline, but you have to do all the math for the world independent of projection. Okay, now the last step that happens here, of course, is if you kind of dig in here and you look at this, and I know, Kyle, you know all about this, right? If you look on the side, it's really far away. So what people do is they bend the monitors in. And if you bend the monitor in, what's happening is you're looking at this distorted world, right? The sides are stretched because if you back out a little bit, and kind of look at this thing, if I can get it, the game, again, and the projection that was originally done had no idea that the monitors were going to be bent. Okay, so now the right way to do this, as we said last night, is to turn on our magic SMP. So when you bend your monitors, what's actually happening is you're opening up the window into the world. It's a much wider field of view, and the sides are no longer distorted, right? We showed you the demo live. And if you come in here and you just look around, it's kind of amazing, right? And if you imagine moving your view inside of the game, you're just moving around in a gigantic window. So it's a very simple idea, but it's powerful implications for the way gamers are going to kind of enjoy their PCs.
So Tom, can I interject for
yes.
1 second here? Okay, so I think this is the one of the points here is this is now we're introducing this idea of multi-projection, right? So one projection, actually, could you go back to the single projection thing there, right?
This one?
Just with the single display.
Yes.
Right. So projection is fundamentally you have an eye point, and you have one, and you're looking off at a point. That's basically one projection, right? So then I go to the other one there, Tom.
Sure.
So this is really still one projection because you're fundamentally looking at the same distance. And then if you go back to that other one, Tom, this is where now you actually have 3 projections because fundamentally, you have one projection that's pointing out that way, but the one off to the side is now a new projection. So it's a different projection. So you have a different projection matrix you have to deal with in the design, right? Because it's not the same point of view. It's not going to be the same map as the first one. And then of course on the right is a third projection. So now you have 3 separate projections that the hardware is processing here.
Now the exciting part for me anyway is that the world geometry that you can see out there is of course independent of the projection. So you don't really need to rerun the world like you do today on classic designs, right? Middle view and then you do the right view. So it's dramatically improving the performance for that type of application. Continue, all right, here we go.
You were on fire, Tom.
Communication. Okay. Now this one's going to be a little bit more complex, so I'm going to go as slow as you'll allow me. So what you're looking at here is the VR use case. And as Jensen said last night, the first thing that jumps out at you, or jumps out at me, is that we can actually do 2 viewports, or 2 projections, 2 completely camera points in stereo at the same time. We call that single pass stereo. It's a capability of SMP. So what single pass stereo means is that as we're going through the pipeline, we're going to be able to actually generate both of these independent positions at one time. Now that's a capability on top of the fact that we can transform these projections. So if I drop the lens for a second, let's start talking about VR in general. You all know why there's 2 projections, right? It's because 2 eyes, right? So it's pretty straightforward. The question is, what do you see? Well, inside a VR headset, hopefully you guys realize there's a lens. The lens is in there so that you can focus on a screen that's 2 inches in front of your head. If you didn't have the lens, you'd feel like you can't focus, everything looks blurry, and you get headaches. So the big invention of this time's worth of VR is that lens. Now if you think about it, lenses by their nature distort. So I'm going to simulate a lens here. Now again, this is just a simulation, it's not perfect. But if I move this lens around, look at what's happening to the image. The square here represents what you would see at the back side of the lens. And if you look at the square, right, as I rotate the view around, you see that sort of pin-cushiony looking distortion? That distortion is caused by the lens. Okay? It has nothing to do with us. It's just optics. Now, the way VR today works with this is they bend the image and they render this full size. So let me drop the lens again. So you're going to render this full size image and then you're going to bend it and you're going to shrink it down. And that really is waste, right? Because you rendered this full rectangle and you're going to bend it in so that you can effectively match the distortion of the lens. So a better way to do it is what we call lens matte shading. Indeed. So lens matte shading looks exactly like this, right? We're going to, instead of bending, maybe, let's see, please stand by. Yes. Okay, instead of being square, we're going to distort the projection, both projections for the left and the right eye, and we're going to create these shapes that look exactly like the eventual lens distortion filter that you're going to run. Okay, so instead of rendering this full rectangle, now we're actually going to render just the center part, right? Only where there's a projection do we actually do work. Okay, so that's pretty clear, right? Now, at the end of the day, the cool part is if you put a lens on this again, and you look at it, you're rotating around the world with our now, call it SMP, lens matte shading shape for the projection, and you can see that it's completely correct. And the big benefit is a little bit better quality, but mostly it's more efficient work. Okay, so for VR, we've got these two things. We've got this single pass stereo and lens match shading. Both are part of SMP.
So Tom, actually, I want to make sure people can see the sort of how the multi-projection is working here. So could you kind of flip over to the side so we can look at those lens shapes a little bit, or the projector shapes a little bit?
Of course.
Okay. Yeah. So you can kind of see here that that shape is basically like 4 tiles, effectively, right? So what we're doing is we're trying to approximate the desired projection for the lens. So the projection you want, the perfect projection basically would be actually this kind of this curved shape. It's a little bit curved, kind of like a lens is curved, right? And you want to ideally approximate that as closely as you can. Now, obviously, a single projection, like we would normally do, is a very poor approximation of that shape, right? It's correct in the middle. If you go off to the sides, it's not matching that lens shape at all anymore, right? And this shape with these 4 tiles, 4 separate projections, one sort of tilting off this way, one off this way, one off this way, one off this way. Now you have a much more accurate approximation of that lens shape. And the more accurate approximation lens shape, the more efficient you're being in the design, because you're not oversampling unnecessarily in the periphery. You're starting at a very good point. Okay.
I think that concludes my prepared remarks. Yeah, all right. Any questions for anybody for Jonah on this? And let's go back to slides.
Yes.
Why is it limited to 4 per eye, not 8 per eye? Because the GPU can do 16.
So we can do more. We're playing with it. So I think that there's we can do 8. We can actually do 16. We can do 16 per eye actually. So you can do 16 on one eye, and then the stereo is actually a free step you get on top of that. But this was sort of the easiest thing to get started with right now was 4, but you can keep going. As you go towards more, you'll get a more closer approximation to that lens shape. Yeah. I'm sorry?
How close is 4 the sphere you want to there? How much extra work does it have to do?
I think I'm going to...
Hey, Jonah.
Yeah.
Whoa, sorry.
Yeah.
Can you repeat the questions as they
Yeah, sure. Yeah, so the question was how close is our approximation to the final sphere? Off the top of my head, I think we're like maybe... Well, actually, let me talk about that a little bit later. I have another slide here, and I can try to get to that topic. But if I forget, then tell me. Yeah. Sure. Yeah, especially when we do anything with curved monitors. So we certainly are capable of doing that. So you could do, you could take 16 projections, and you could, if you have some sort of like super wraparound monitor, you could line all those up, so you're basically rendering it directly. So yes, we are capable of doing it. Yeah, I think the software team's focus right now is number 1, covering that surround monitor case. So they've done that. And then number 2, covering the VR cases. But again, as I said in the slide, lenticular is an interesting case. Surround display is an interesting case. Crazy dome things. There's lots of interesting cases to think about.
So I'll add. Sorry, Jonah. One of the cool things about SMP is that it's actually just available for developers to program themselves. So it's just a capability at an architectural level. So the developers can do crazy display stuff, as they see fit, right? They can program the viewports, they can program SMP and lens map shading, they can do that. So if they want to do a curved monitor, or they want to do a geodesic dome or whatever, that's available for them to do as well. They don't necessarily just have to wait on us. Yeah. Oh yeah, and Jason said, and we're putting an SDK out so they can just make use of it directly.
Okay.
I'm supposed to say who I am. I'm Tony Tomasi. I'm the SVP of content. So sorry.
Yeah, so
You'll hear from me later.
We're going to do some Q&A in the end, but I think it is good to just take some Q&A right now. That's okay?
Yeah.
Fish, so yeah, okay. Yeah.
Presumably for surround monitors, you'll need to know the angle of your monitors. Is there any way to calibrate that using an on-screen tool versus using a projector?
Yeah, so the question is basically how do people calibrate the monitor angle for surround display?
So we actually have a mechanism that's basically in the control panel that you can do basically a visual alignment, where you can adjust the angle of your display, which adjusts the angle of the projection at the application level, so you get essentially a perfect projection that can match your display angles or tilts or whatever. And it's a pretty easy kind of a grid-looking field to do that. So we just kind of built that right in.
Okay, so let me try to take a couple. Yeah, sure. Yeah.
So are you going to talk a little more about how you did the multi-projection?
Yeah, so yes, this is the last slide. Actually, why don't I go through my architecture slides a little bit more, and then we can see what questions you'll have after that. Is that soon? Okay. Yeah.
Back here before we.
Yeah. Okay.
When you showed the distortion, I think you said you're basically creating 4 tiles.
Yeah.
You put distortion and line boundaries there. How do you avoid that when you change the shape of the image?
So you mean the boundaries between the different between the different projections? Is that what you mean?
When the angle changes in the projection, how do you avoid the image sort of sliding along the angle at
right.
visually perceivable?
So let me try to answer, and anyone can interrupt if you want. So with that example, the sampling is both C0 continuous, meaning that at that point of junction, you're sampling in the same point between the two sides, between the left and the right projections, right? Because they're the projections are abutting each other. So, and then also the sampling rates are also going to be matched at that point. So the sampling rates are continuous. You still have to do a lens warp, right? So this is an approximation of lens warp. It's not an exact match to it. So there's still going to be the same lens mapping pass in the end, where you go do a lookup from this tent shape and you map it into the curve shape. And then at the end of the day, it's going to look the same as if you'd drawn it with a flat thing. You just have to do different math in order to get there. So any more questions just on the whole projection concept, and then I can go up into architecture. Say. Okay, I'll keep going. We can. Okay. Okay, so then now this is sort of going a little bit into the implementation now, right? So what I've drawn on the left is basically sort of the canonical graphics pipeline, right? With the multi-projection added into it, and just showing where it happens in the pipeline, right? So the classical pipeline of that multi-projection is you have your input assembler where you pull in vertex attributes. They'll go into the vertex shader. The vertex shader takes these objects like the cube that was in Tom's demo, and goes and positions it from being in an abstract place to being where exactly it is in the screen and scaling it properly, right? And then of course, as the graphics API has moved onwards, we've added more enhancements in that stage. So you can do tessellation. You can take a set of control vertices and sort of fill it out with more detail. You can do a geometry shader, which can actually take primitives from that and expand them out and do different other things. And then what would normally happen is you would then take that final triangle, it would go into the triangle setup engine, which computes some equations related to the tilts and angles of those things, and you go ahead and rasterize the pixels, right? And if you want to do more projections, well, projection is basically kind of baked into the vertex shader setting things up, and then we have sort of one unit that knows what one projection is and just does that projection. That's normally how things would work. And in this generation, we've now added the simultaneous multi-projection unit, which knows about up to 16 projections now, and has the ability to expand, which would not have existed otherwise, right? So now you can have one triangle that comes in, and this multi-projection unit takes the triangle, and it has its own knowledge of all the projections that the user wants, and it'll go say, okay, let's say if you have all 16 turned on, right? It would just go through each projection and say, okay, project this triangle to this projection, project the next one, project the next one, project the next one, project the next one, and then it goes on down the pipeline where the rest of the design also knows about these different projections and knows where the pixels are supposed to go based on that. And this unit is basically embodied in the polymorph engine that we have, where we have one polymorph engine per SM in the design, and we have the units we've had before, and now there's this new unit which basically pulls in this functionality along with kind of the older functionality that exists related to projection is now slurped into this multi-projection unit. And I think that is the. Oh no. Okay. So I have some performance numbers here. Okay. Cool. All right. Yeah. So I want to try to kind of put it together into an example of sort of what this gives you performance-wise, right? So on the left, I'm talking about the pixel throughput part of it, right? So with an Oculus Rift, your initial rendering is going to be about 4.2 megapixels between the two eyes, right? And then again, that's in the side it's really oversampled, but that's all you can do in order to get the middle to be sampled correctly, right? So one of the ways that we're looking at this is saying our starting goal is to is to try to match that final resolution of the display that goes into the lens, right? You can also undersample, of course, and you could think about maybe that being interesting to do in the periphery of the scene where it's harder to see resolution. But we don't want to do that, right? So the conservative preset that we define is a preset where at no point in that screen are you sampling at a lower rate than the actual resolution of the screen itself. So with that setting, what you see is an image that all those black pixels in the periphery are no longer have to be shaded anymore. So you've reduced your number of megapixels you have to draw. And with this preset, it's about a 2.8 megapixel is worth we have to draw instead of 4.2 megapixels. So the way to think about that is you effectively have 1.5x more horsepower available to you for pixel throughput than if you rendered it, in this blown up way. And I think somebody asked a question about how close is this to the sort of the speed of light, I guess, the exact match. Let me look it up later, and maybe if people that wanted to could email Nick and those guys. But I'm going to say off the top of my head, I think we're like maybe 20%ish above what the actual final resolution is. So we're not exactly matching it, but we're matching it pretty close. And as someone was asking earlier, this is just with 4 projections, but we can go to 5, we can go to more. Their developers can also play with that. So it's possible to match it at even finer grain than that. So let me go to the next thing, and then we can see if we have other questions about multi-projection. So that covers the pixel side, but as I mentioned before, there's also a geometry workload issue, right? The way that all GPUs work today doing VR is that you draw one eye, all the command stream, all the push for generation, everything goes down to the GPU for one eye, and then when you're done with that, you do the whole thing all over again with other eyes. That whole top end of the pipeline is done at 2x, right? Well, with this capability, because not only do we know about different projections that are tilted, we also can know that projections have a different x value. We can shift projections around, right? And because we can shift projections around, you can just send us one set of geometry and tell us about the 2 shifted eye locations you want, and we'll be able to do that expansion in that multi-projection unit to basically send it out to 2 eyes. From the geometry side, I picked the Barbarian demo yesterday. Effectively, for VR, you're only seeing one Barbarian with your eyes, but from a geometry perspective, we drew 2 Barbarians, right? We drew the full geometry once and the full geometry again with the simultaneous stereo. What is it? Single pass stereo. Yes, single pass stereo. Thank you for that. With the single pass stereo, we only draw that once. Actually, one thing I want to say on this point, sort of just to bring up some other sort of technology in this area, right? So people have been thinking about some of these issues. There's a thing called instance stereo, I think, right? So instance stereo is this idea, but only on the CPU side. So instance stereo is the idea that you can basically construct one push buffer, and then you can basically send 2 instances of that down to the hardware. So on the CPU side, you've saved that work. But instance stereo doesn't do anything for you on the GPU side. The GPU still sees 2 full sets of work and has to do 2 full sets of processing. So whereas that doesn't have any savings on the GPU side, which is of course where the heavy lifting is happening, this single pass stereo has the full savings of work there. So that's how it's distinct from that technology. Another technology, which something that we brought up with Maxwell is Maxwell had sort of a prototypical kind of step in the spectrum towards multi-projection, which we call multi-resolution. So multi-resolution is you only get one projection, but you can change the resolution of the size of that projection. So with that, you can do a little bit of this stuff basically, and with multi-resolution, because you can't tilt anything, you can't get super close to fitting that lens, but you can at least sort of pull the. If you imagine kind of this like dome here, you can kind of pull the sides down at least until the point that they touch that shape, and then you can't pull them down anymore. So with multi-resolution, we can get kind of a 10 to 15%, I think is the math we're looking at, savings for the Oculus lens. So we get sort of interesting some savings, but not a whole lot of savings. With this, because we're able to really tilt the angles, we can do a much closer fit. We get a much better savings with multi-projection. So that's the distinction between these two. So I think that's what I have for this. But let me ask if there are any other questions on this one before I keep going.
I have an injection. Can I inject?
Yes. Tony, go ahead and inject.
Yeah, so you can actually use these technologies beyond VR applications. In fact, in the demo room in the back at break, you'll be able to see a developer, Cyan, implemented this in their game Abduction, which has a desktop or a normal PC implementation, and they did it to do what I'll call it a pseudo-foveated rendering, is maybe one way to think about it. They render the center of the screen at full resolution, and they render the periphery of the screen at slightly lower resolution. It's essentially imperceptible in terms of image quality, and they get about a 40 to 50% performance boost out of it. So check it out. It's pretty cool. I think there's going to be a lot of really interesting applications of it, because there's lots of people who are questing after the perfect 60 hertz sustained frame rates, and they're willing to give up maybe a few percent of the pixel resolution at the very edge of the screen, because that's not usually where the player's looking. They're usually looking at the crosshair over the shoulder of their character or something like that towards the center. So you can check it out and let us know what you think. But it's pretty promising, and I think developers are going to find all sorts of really excellent ways to take advantage of this for gamers. So
yeah, so that's a good example of a classical multi-resolution application, right? That's a single display. You're projecting out this way, but if you reduce resolution in the periphery, you can get the savings. That's a good demo of that technology. Which again, that's technology that both Maxwell and Pascal have. So yes, okay.
Yeah, Jonah, what extra hardware would you need for SMP to work within Pascal?
Within Maxwell, you mean, or
Sorry,
within
Pascal. So what extra hardware do you have? In other words, why
Right.
can't it be backported to Maxwell?
Yeah, so the key thing is you need that block, right? In a classical graphics pipeline, there's a concept of that whole pipeline of there being one projection, and there's no way to expand out after the shader stages to just throw out the multiple projections. That's the definition of the pipeline, right? So basically, that's the change we made, is to add this new expansion stage and to give that stage this knowledge, which didn't exist previously.
Yeah.
Question right here.
Yeah. Okay. Yeah.
So can we say this SMP feature is programmable rasterizer? If yes, how do you expose this feature? By a new shader model or just OpenGL extension?
Yeah. So I guess it's you can look at it as sort of like a programmable rasterizer in the sense that the effect is you're basically varying your sampling rate. But the way it's done is by varying the projection, right? So like if when we tilt a projection this way, like this, it has the effect of changing the sampling rate for that side. But the way it's programmed is by changing projections. And I guess to your question about how it's used, I think maybe if somebody like Tony could interject or something like that on the mic. Could you repeat the question for Tony's benefit there?
So the question was, how do you access it, or how do you program
Yeah,
it?
Right.
by new shader model or the OpenGL
so-
extension?
Yeah.
although I can be loud without a mic, but I sound cooler on a mic. So
Uh-huh.
we have an SDK. There are forms of this can be accessed through extensions through OpenGL, some of which are actually already available right now. We actually have an SDK which we're going to publish, which basically makes calls directly to, I'll call it our instruction set. This isn't currently part of, a DirectX shader model X, Y, or Z. This is something beyond that capability. This capability will be available, accessible from any of the graphics APIs, be it OpenGL, Vulkan, D3D11, D312, whatever.
Okay. Yes.
Is the increase in performance, or I'm sorry, I guess the decrease in performance linear as you increase the number of multi-projection windows?
Sorry, is
So as you add more multi-projections, is
Right.
is the performance required to render them? Is it a linear increase?
It should be, performance should be a function of how many pixels you're shading or how many triangles you're actually processing. So
When you go from just 1 to 2, are you doubling the number of pixels you're shading and the number of triangles you're rendering?
So it's intended to be an almost free feature, okay? And what I mean by that is, let's take the multi-resolution case that Tony example mentioned earlier, right? If you have a single display, you just chop that display in half, right? That in that case, half the vertices, half the triangles end up on one display, half the triangles end up on the other. But you're not really sending that many more triangles down the pipeline, right? If you have a triangle that splits between those two, then that triangle would then go to the downstream, but it wouldn't go very far downstream. So basically, there's very little overhead to do that. And then at the end of the day, on the pixel side, it's about how many pixels you're drawing, right? So if your screen was this big and you did a multi-projection, chopped it in half, but the same number of pixels were being drawn, then it's going to be the same the same workload. Now, of course, the intention is you use this to accelerate what you wouldn't have to do otherwise, right? So if you wanted to have, for example, a surround view system, now that would have been 3x, right? One projection for each display, so you're going from 3x to 1x, so you've saved 3x the workload in that case. Or in the case of VR, where the final pixels you're being rendered are maybe let's say 60% of what the original rendering resolution was, right? So there's all these pixels being thrown away, right? We throw much fewer pixels away because we can approximate the design better. Does that sort of answer that, or?
Yeah, I think so. And then, so taking that to the extreme, though, if you're kind of getting it for free in a certain sense, for the VR use case, would the theoretical ideal be almost like a per pixel per multi-projection?
Yeah, that would be, I guess, the speed of light, I guess, would be that, if you just perfectly matched that lens shape, right, then you would be, there'd be no waste at that point, right?
And sorry, quick final thing. What is limiting the current number of projections to 8 or 16, whichever it was?
So the limitation is because that's what this, right? This is a hardware unit, right? So you can only do what that hardware unit knows about, right? So that hardware unit knows about 16 projections and it knows about stereo, so that sets what you can do. And I guess to your question of like, why not 32 or 64, 128? If you cross the boundary, you do have to do that triangle twice. So as you get finer and finer, you are doing somewhat more work, and your benefit starts to diminish at some point, right? I mean, we're with only 4 projectors, we're actually pretty darn close to what the speed of light would be. Throw in a few more, you're probably close enough at that point where the benefit of going beyond that wouldn't be super high, versus as you go forward. I mean, in the infinite case, you would be getting more overhead. So we wanted to put in. So we wanted to put in enough that we felt people could have a lot of fun with it, basically, right? And I think 16 is a pretty good number. I think we'll be able to do a lot with that, and that seemed like a good number for us to put in. So. Okay.
Thank you. With this, would you be able to run the same scene on 2 different VR headsets, looking at it from different angles?
I think you could do that. Yes. Tony, yeah.
Thanks, Rick.
Two different angles. Well, no. Okay, so let me say what you can do, and I don't think it's quite what you. So we can do multi-projections from one eye point, right? So if my head is here, I can project out, all around this dome, right? Now, if you have another viewpoint, that's a different deal. So we wouldn't do that. So if you wanted to do, from one viewpoint, letting a lot of people look around a point, you could do that. But it has to be a common source position, with the exception of the stereo thing. Lets you put your eyes in different places.
Okay. Yeah. Are there any improvements to the polymorph engine besides simultaneous multi-projection? Maybe it's higher primitive throughput.
So per engine, this is the main change that we have in this generation. Obviously, we have more of them and we have higher clock rates than the 980, so that gives you a lot more throughput. But from an architectural standpoint, this was the big change we made to each instance of the engine.
Okay, but the throughput per clock stay the same.
Yeah, right? Throughput per clock per engine is similar to what it was in the Maxwell.
Okay, thanks.
Okay. Yes, Ryan. Yeah.
All right, so this may go a little too deep here, but can you explain a bit more how this differs from multi-projection acceleration in Maxwell 2?
Yeah.
You had the same general idea here. Viewport multicast, single pass, doing Bach generation.
Yeah. So the Maxwell, as I mentioned, so we had multi-resolution in Maxwell, right? Which is basically that you can, in one projection, you can change the resolutions. We did also have a very constrained ability to to do a cube, right? But it was strictly 90-degree rotation, so it wasn't really useful for this, right? So this is now you have this full degrees of freedom to rotate your viewport any way you want. So that's why what we had in Maxwell didn't really apply to this application. Yeah. Okay. Yeah.
Does SMP also help with rendering things twice if you want to watch a game both on your VR headset and want to have a 2D output, for instance, for streaming?
That's an interesting idea. So yeah, I think that you could do that. I think, right, Tony? Because so that would be basically a single. Yeah. So what you're saying is, I have a single viewport. I'm playing the game, right? I want to see. I'm looking at it in VR, so I want to see my eyes in VR, but I also want to see a 2D view to capture it for streaming. That's all from the same viewpoint, so yeah, I think we could.
Yeah, as long as it's the same origin, same viewport origin, you could do that.
Yeah. You guys are writing these ideas down, right, Tony? Man, this thing's,
by the way, that's
thing's getting better every minute.
Is that you guys and everyone will come up with great ways to do really innovative things, and we can't actually wait to see what everyone does with it. I mean, that's kind of the point of making this flexible, programmable thing, that people are going to come up with ideas we didn't think of, which is awesome.
Yeah. Okay, so why don't I'll take one more question, then I'll let you keep going here. Is there another question, or?
Good.
Okay, all right, cool. Okay, so let me keep going. Cool. Okay, so that's simultaneous multi-projection.